Hi everyone, welcome back. We are still in our section of why do we give a crap. This time we're just going to add some math. Let's get practical. How do we use this concept of a mole? Oh, I feel that the mole needs a sparkle pen. Okay, how are we going to use this concept? So for this video, you need your periodic table, preferably the one I handed out in class, but any of them will do. We just need some atomic weights, and you're going to need your calculator. Let's take this idea of a mole and let's use it. Okay, so the first thing, let's do a little refresh on our definition. So our definition of a mole as of the 1980 version, and then I'll probably use the more current version, was for carbon-12, 1 mole gives us Avogadro's number. And the 1980s version would have called that a particle. The 2019 version calls that an elementary entity, which I am going to coin the phrase and just abbreviate EE. How's that? Even though to an organic chemist, EE is an enantiomeric excess, let's just go with it for the sake of our videos. Okay, so our 2019 definition, I'm just going to abbreviate here. Okay, so what is our elementary entity? In this case, that would be atoms of carbon-12. And then how much does that weigh? 12 grams. So why is this so important? This is something we can easily measure in the lab, and now we get our count of atoms. This is awesome. This is why the mole is so phenomenally important in chemistry, and probably by far one of the most important sections of this entire semester is that relationship of a mole. And then we recognized in the last video, wait a second, it doesn't have to be only carbon-12. This actually works for all of our elements. And we're going to start making compounds as well. It works for everything on the periodic table. So let's just do a little practice. This is awesome news because no matter how you slice it, these are really just one big fancy unit conversion. That's it. So on the periodic table, anytime you see an atomic weight, the unit for that atomic weight is grams in a mole, which translates to grams over mole. So every single one of our atomic weights now on your periodic table, write that down. You now have grams in a mole for every one of them. This is genius because remember, all of our elements are different. They all weigh different. So in order to have the same number or have our count of sodium equal our count of chlorine, which we know we need. We know we need that from our unit 2 bonding. We have to have 1 and 1. How are we going to get that count? That means that our moles are going to end up equal. Those moles are going to give us the count. And then we can figure out how much to weigh out in the lab. All right, so let's do some practicing. Bust out your calculator. Let's just take sodium. Let's take sodium and let's do some unit conversions. My goal after this video is for you to maybe be able to tackle that first homework or at least part of that first homework. So let's kind of scroll up and give ourselves some space here. Okay, let's take sodium. If you've got 22.9989 grams in a mole, and that is equal to your Avogadro's number of atoms. Atoms is our elementary entity. Okay, so this is awesome. Now, if we want to compare that to chlorine, this time chlorine is 35 grams, not 23 grams like sodium. It's heavier. So 1 mole of our sodium is going to be 6.022 times 10 to the 23rd. Our EE is still atoms. Awesome. So what just happened here? We just cracked the code. We have the same number of atoms of sodium, the same number of atoms of chlorine, and then our actual atomic weight just told us how to go to the lab and make sodium chloride. So what would we weigh out? We would literally weigh out 22.9989 grams of sodium. Okay, I feel a little orange pen coming on. And then we would mix it with, oh, wrong pen, son of a, we would mix it with that 35.455 grams of chlorine. And then Mother Nature does the rest. And what does that make? Literally, you mix these two amounts and you just made sodium chloride. Okay, now here's the trippy part. You just added 1 mole of sodium, 1 mole of chlorine, and you made sodium chloride. So what is your new definition of a mole? Your mole doesn't have to be only atoms. Your mole can be molecules. So if you have a mole of sodium chloride, let's see if we can figure that out. Let's take our sodium chloride. Okay, we just made something new. Let's say we have a mole of sodium chloride. How many particles are you going to have? How many molecules did you just make from that reaction? Well, you had 6.022 times 10 to the 23rd over here of your sodium, 6.022 times 10 to the 23rd of your chlorine. Except once you mixed them, you literally stuck them together. So now this mole of sodium chloride is just like baking cookies. These were the ingredients, sodium and chlorine were the ingredients. Now you stuck them together. So your actual particle now, your elementary entity, is now that whole molecule. And how many of them did you make? You made 6.022 times 10 to the 23rd sodium chloride molecules. Okay, now here's the super fun part. Okay, you literally took those, you stuck them together. Okay, and now, wait a second. Oh, I shouldn't erase so much. How much does that 1 mole weigh? Well, didn't you take your 22.9989 grams, literally mix it with 35.455 grams? You did. Grab your calculator. How much does your new particle weigh? It weighs those 2 atomic weights. So let's add that up. I'm going to grab my calculator too, because if we were in class, we would stop right now. I would not have my calculator, but you would, and you would tell me the answer. So let's add that up. And I get 58.4539 grams. Now, what's the unit for that, and what do we call that? Our unit is still grams in a mole. That is going to be 1 mole of that sodium chloride, so let's write that over here. Okay. And now, what did we just make? That's not an atomic weight anymore. This has 2 names, but only for Gen Chem 1. Everything after this, it will be called a molecular weight. And I will call it a molecular weight, but occasionally in a Gen Chem text or sometimes an Intro to Biology text, it will call this a formula weight. And what's the difference? Okay, let's hit some vocab here. Formula weight is for ionic molecular weight is for covalent. Even though by the time you get out of Gen Chem 1, everybody just mixes and matches and they end up calling it a molecular weight anyway. But just for Gen Chem 1, they're called either one of those. Probably in my homework, I call everything a molecular weight. Okay, so that's trippy. So let's do a quick review before we go on there. All right, we started with just sodium atoms. I remember the definition of a mole of anything. It doesn't matter if it's atoms, it can be molecules, it can be anything, any elementary entity, and you will have this same Avogadro's number count. So we took 1 mole of sodium and we mixed it with 1 mole of chlorine, 2 separate things. And then when we mixed them together, they combine, ionic bond, and we made a whole new compound. Only now the actual particle is the sodium and the chlorine stuck together, sodium chloride. So now this is a molecule, and we use a molecular weight, and it is the sum of your atomic weights. Okay, and we now have a whole new particle, or EE, and it is a molecule. So we do the exact same math for atoms as for molecules. You just have to keep in mind what is your particle or what is your EE. Is it an atom or is it a molecule? So we can do all these literally like a unit conversion. So let's write one down here. So what if you are absolutely destined to get an A in Gen Chem? Because of course all of you are. So you go to the lab and you want to make your sodium chloride, and son of a motherless goat, you don't have 22.9989 grams. You have 10 grams of sodium sitting there. Are you totally screwed, or can you still make salt? You can absolutely still make salt. This is where the unit conversion part comes in. If you have 10 grams of sodium, it just means you don't have 1 mole. You're going to have less than a mole. So we can use our atomic weights as unit conversions. So let's do the same thing that we did in Unit 1. And let's let our units do the talking. So what do you want to figure out? Well, if we don't have 1 mole, how many moles do we have? Put your grams on the bottom. Put your moles on the top. And then what do you plug in here? You plug in your atomic weight. Let's use our green. So our atomic weight then is the 22.9989 grams in a mole. We get to cancel just like our unit conversions. Bust out your calculator then. I'm going to pause for a second and calculate myself. What is 10 divided by 22.9989? Aha. You have, ooh, are we back to sig figs? What? All right, how do we fix this answer? We have 3 sig figs here. Let's put 3 here. Let's put, for funsies, just like we were back in lecture, let's put a little harder on that. Instead of having 1 mole of sodium, you're going to have 0.435 moles of sodium atoms. Okay, now this is still a count. It doesn't have to be 1-to-1. So if we wanted to still calculate, well, how much chlorine would we need to have that same amount? Can we do that? I mean, if you're about to make salt from that, you don't want 1 mole anymore. How many moles do you want of chlorine? You want 0.435 moles of chlorine. Ooh, I feel another unit conversion coming on. Let's give ourselves some space. And let's take that and let's redo it for chlorine. Okay, so we just took sodium and converted that to moles. If we wanted to go ahead and do this reaction and make sodium chloride, we know we need 1-to-1. So let's take that 0.435 moles of sodium and let's recognize that we need the same moles of chlorine. So that is 0.435. Okay. And then let's take that and convert it to grams. That way we know in the lab what we're going to weigh out. Awesome. All right, so then let's fill in that atomic weight. I think for chlorine it was, what, 35.455 in 1 mole. So let's multiply. Me too. All right, I get 154 point. That just doesn't seem right at all, does it? See, this is why I need y'all in lecture. Let's try that again. 0.435 times 35.455. There, we're talking turkey. I get 15.4222925. So what would be my units? Grams of chlorine. How do we fix that? How many sig figs do we need? 3. Look at that. So what did we just learn? If we wanted to do that reaction, we would take 10 grams of sodium and we would mix it with 15 grams of chlorine to make our sodium chloride. Okay. All right, so our mole is going to end up in the middle of all of our calculations. We definitely want to practice a lot of these. They are one big fancy unit conversion. So we've got, let's do another one. Let's take carbon and hydrogen and make methane. We did this in unit 2 also. All right, so if we've got carbon, let's just write out what we know already. I'd like to make one big chart so that we're pretty solid on what our concepts are. So if we've got carbon and we take 1 mole, that 1 mole is Avogadro's number. And we've got 12.011 grams as our atomic weight. This is our atomic weight. Okay, perfect. Let's do the same thing for hydrogen. If we've got 1 mole of hydrogen, that's giving us Avogadro's number. And that weighs our atomic weight. Perfect. So now we know from our covalent bonding that if you actually mix carbon and hydrogen, you're going to make methane. Okay, so now it's not 1-to-1 anymore, is it? Oh, the plot thickens. So let's see if we can figure out how this would work. All right, let's take our molecule, carbon and methane, and let's go ahead and write out what we know. Let's take 1 mole of our methane. All right, how did we put together that 1 mole of methane if we started with 1 mole of carbon and 1 mole of hydrogen? Well, those together would make what? CH. Oh, but that's not what we have. If we were to mix that together, Mother Nature would stick that together and realize that you actually need 4 of those hydrogens for every 1 of those carbons. Remember, this is still following a bonding rule for what we are doing. So how is that gonna work? Well, that means for every 1 mole of carbon, how many moles of hydrogen are you gonna need? 4. Oh, okay. So now in our particles, that means that we are going to take that 1 mole of CH4 is actually 1 mole of carbon atoms and 4 moles of hydrogen atoms. Hey, I need to pause for a second because I'm worried about my video. I may come right. Well, it says it's still recording. Let's just keep doing it. I'm going to stop after this question, though, and do another one. Okay, so now I just mix those two, and we've got 1 mole of carbon for every 4 moles of hydrogen. Well, we already know the answer to this, right? If we have 4 moles of hydrogen, then each one of those moles is 6.02 times 10 to the 23rd. And how much does that weigh? This whole thing then times 4. And then for carbon, we get to keep our 1 mole, and that is our Avogadro's number. And then how much does that weigh? So then if we want to go back up here and fill in for our methane, 1 mole of methane, how much is that going to weigh? What's going to weigh 12 plus 4 times our 1.008. So let's take a second. Let's do that on your calculator. Okay, 12.001 plus 4 times 1.008. And I am getting 16.033 grams for that mole. Okay, how did I do that? I added this plus that. And then here's the tricky one. How many actual little elementary entities do you have here? You are going to have 6.022 times 10 to the 23rd molecules of methane. I'm going to stop this video, but we're going to do another one of these.